You know, deep inside the massive machines that power our world, there's a hidden danger lurking. It's a silent, invisible threat that can bring a colossal hydrogenerator to a grinding halt with basically no warning. So how do you even hear a problem before it happens? Well, let's dive in and uncover the science of listening to our machines to prevent a total disaster. I mean, just think about it. Hydro generators are absolute engineering marvels, right? They're the true giants of our power grid. But for all their incredible strength and scale, they have a surprisingly delicate heart, their electrical insulation. And it's right there that a very subtle process of decay can begin. And look, we're not talking about minor hiccups here. This silent decay can lead to a sudden, catastrophic failure while the machine is running. Can you even imagine the immense cost and disruption when one of these giants just unexpectedly goes offline? So the really crucial question is, what's causing this, and how can we possibly spot it before it's way too late?
And the scale of this problem? It's staggering. A major survey by Seagray back in 2009 found that issues with the stator insulation, that's the protective stuff around the generator's core wiring, are responsible for half of all forced outages. That's right, 50%. This isn't some rare thing. It is the #1 cause of failure.
So, the old way of doing things was, shut everything down for an inspection just because the calendar said so. But the modern approach, condition-based maintenance, is just so much smarter. It's all about listening to the machine, predicting problems, and then acting only when there's a real sign that a failure might be just around the corner. All right, so what is this invisible threat, this silent symptom that engineers are trying so hard to listen for? Let's get right to the heart of it. It's called partial discharge, or PD for short. The best way to think of it is like tiny little lightning storms, small electrical sparks that are happening inside the very insulation that's supposed to be containing all that high voltage. These sparks are a direct sign that the insulation is getting old and starting to break down. And this right here is the key idea. A brand new, well-made stator winding is electrically quiet. You get very little partial discharge activity. But as it ages and deteriorates, it starts to get electrically noisy. It begins to whisper with these tiny sparks, and those whispers just get louder and louder over time. And we're not talking about a subtle change here. The increase in PD activity is dramatic. It can jump by a factor of 10 or even more. And that's exactly why it's such a powerful warning sign. It's a huge, unambiguous signal that something is seriously wrong. Okay, so we get what partial discharge is, but why does it happen in the first place? What are the real root causes that kick off this whole process of decay?
Well, it really all boils down to stress. I mean, this insulation is under constant attack from all sides. You've got mechanical stress from vibrations, thermal stress from high temperatures, chemical attacks from things like oil or moisture getting in, and then just the general wear and tear of time. All of these things create tiny little voids and cracks in the insulation, and that's what gives those partial discharges a place to spark.
All right, so we've got these tiny sparks happening deep inside a massive, spinning, high-voltage machine. The next logical question has to be, how in the world do you actually detect them? Let's look at the really clever tech they use to listen for these whispers. And that really is the challenge, isn't it? A power plant is an incredibly noisy electrical environment. You have signals flying around from all over the place. So how do you isolate that one faint signal of a partial discharge from all of that background chaos? Well, the solution is all about tuning in to the right frequency. The older methods used lower frequencies, but the modern approach tunes into the very high frequency, or VHF, range. Why? Because it turns out that above 40 megahertz, the signal from the actual discharge is way stronger than the background noise. It's kind of like finding a quiet channel on the radio so you can finally hear the broadcast clearly. But there's another really clever layer they use to filter out the noise, using a principle called time of flight. So imagine you have two sensors on the machine's wiring. A random electrical pulse from outside the generator is going to hit both sensors at the exact same time. But a real PD spark, starting from inside the winding, will always hit one sensor just a few nanoseconds before the other. The system sees that tiny little delay and knows, aha, that's a genuine spark. It's brilliant. Okay, so we can reliably detect these sparks. Now comes the most important part, using all that data to see into the future and predict when a generator might be at risk of failing. This is done through what's called online monitoring. They permanently install these super sensitive capacitive sensors right on the machine. You can think of these as the ears of the system, just continuously listening for any PD activity 24/7 while the generator is running normally.
So what's the data telling them? Well, engineers look at a few key things. They look at the magnitude, basically how intense are the sparks, and the pulse count. How often are they happening? They even use these special plots that map the sparks against the generator's electrical cycle. This reveals distinct patterns that can actually pinpoint the root cause, whether it's from vibration or contamination or something else entirely.
And here's the absolute game changer. This isn't about getting a few days or weeks of warning. In most cases, this monitoring provides 2 or more years of advance notice before there's a high risk of failure. I mean, just think about that. That's a massive window of time to plan maintenance and completely avoid a disaster.
And the financial impact? It's a no-brainer. The cost of a planned repair, based on this early warning data, is just a tiny fraction of what it costs when a machine fails catastrophically while it's running. We're talking a potential cost difference of more than 100 times. It's not even close.
So, what's the bottom line? This smart monitoring totally transforms the whole maintenance strategy. The machines are available more often, repair costs plummet, those catastrophic failures are pretty much eliminated, and maintenance gets done precisely when it's needed, not just because the calendar says so. It's safer, it's cheaper, and it's way more efficient.
It's a pretty powerful idea, isn't it? We've learned how to translate the faint electrical whispers of a generator into a clear forecast of its future. And that leaves us with a fascinating question. What other invisible problems in all sorts of other complex systems are we on the verge of finally hearing long before they ever become a disaster?